Okay, in this video, we want to see what the relationship is between the eigenvalues of a matrix and the eigenvalues of a power of that matrix. And we also want to see what the relationship is between the eigenvectors of those two matrices as well. So before we get into this specific problem, let's say that lambda is an eigenvalue of A. So, of course, we know what that means. It means that A times X equals lambda times X for the eigenvectors X. Now, if I were to now find, for example, A squared X, well, that's equal to A times AX. And then that's equal to A times lambda X. But because lambda is a scalar, I can actually pull that out and just say lambda times AX. And that again would be lambda times lambda x, which is lambda squared x. So notice that lambda squared is an eigenvalue of a squared. Well, you could prove this by induction or some other technique, but essentially a to whatever power you want would have to be lambda to that power x. So in other words, if lambda is an eigenvalue of a, then we could say that lambda to the n is an eigenvalue of a to the n for some positive integer n. So if we just knew what the eigenvalues for this matrix were, we could just raise those to the seventh. But we do. This is actually the example that we did two problems ago. This is the matrix that we showed is not diagonalizable. So from two problems ago, lambda equals 1 or lambda equals 2. And so the eigenvalues for a to the seventh are lambda equals 1 to the seventh, which of course is just 1, and lambda equals 2 to the seventh, which is 128. So that answers the first part of this question. And now we want to see what the corresponding eigenvalues are. Well, notice we've kind of already answered that. So if you look right here, a squared times x is lambda squared times x. That means x is an eigenvector for a squared. But remember, x was also an eigenvector of a. So in other words, if we are raising a matrix to a power, to a positive integer power, then the eigenvectors are exactly the same, and they correspond to the same values. So we could say then that, in fact, for let's say for lambda equals 1 for a, this is again from the same problem 2 back from this, we found that x would equal, or could equal, 1/8 negative 1/8 1. Right? So if that's an eigenvector for a, we could say this is an eigenvector for a to the seventh corresponding to lambda equals 1. And again, this is the lambda equals 1 that we just said earlier. Further, from the problem 2 back, for lambda equals 2 for a, we found that x could be 0, 0, 1. And of course, that means that this is also an eigenvector for a to the seventh, but that corresponds to lambda equals 128. Right? Remember that these were the powers of the eigenvalues from the previous one. So that's actually a pretty easy question. Now that we've kind of see why that works, all we have to do is raise the eigenvalues to the same power as whatever it is that we are finding. And the eigenvectors, they remain unchanged. So the space, I guess we could say the eigenspace basis vectors remain unchanged for regardless of power. So I could ask even something like, a to the 1,000th. What are the eigenspace basis vectors for a to the 1,000th? The answer is it's still these two, right? And of course, for the for the eigenvalues for the same, raised to the 1,000th, this would still be 1. Of course, this would be 2 to the 1,000th, which you could always just list as that. But so anyway, pretty easy problem now that we kind of see how that works. Hopefully that makes sense. And if you have any questions, please let me know.